Bismillahirrahmanirrahim. Dear students, today we are going to discuss on law of mass action and law of chemical equilibrium. First of all, we know a class of reactions, we call those reactions as reversible reactions. Reversible reactions means those reactions which will occur from both sides. Reversible reactions. Let us take this example. For example, we have this reaction A, and this one B, that gives up this one C plus this one as DD. These are the products, these are their stoichiometric coefficients, these are the reactants, these are the coefficients which are involved within the balanced chemical equation. So if this occurs in a reversible way, means when these two reactants they react with each other or leading to formation of products after certain interval of time, means after some time these two products they start reacting with each other leading to formation of these reactants, then we call this reaction as reversible reaction. Means a reaction occurring in the forward direction as well as in the reverse direction. That reaction is a reversible reaction. Mostly the reaction is carried out in closed vessels. They occur in this fashion, means in the reversible fashion. In the reversible fashion, we can say the rate of the reaction in this direction, in the forward direction, we call that as rate in forward direction, and this one as rate in backward direction. Means here I will write constants. This one Kf means this is the rate constant of the reaction in forward direction, and this one Kb, this is the rate constant of this reaction in the backward direction. We already know this rate. Rate is change in concentration, means this one change in concentration of any species involved within a chemical reaction divided by time taken for that change, means divided by time taken for that change. We know this concept in chemical kinetics, that is, if we will take these reactants, we will take reactants, their concentration that decreases with the passage of time, so we will write here negative. If we will take any of the product, then in terms of products we will write here positive, so I will write here plus minus. Whether I will take any reactant or product, I will keep the rate of the reaction in terms of any reactant or product. This law of mass action, it was formulated by these two scientists. First of all, this one, Goldberg, and this one as Peterbridge in 1864. They formulated a law which can be applied to such reversible reactions or even to irreversible reactions. Within this law, its statement is for the rate of reaction. I mean to say, for this reaction, according to this law, rate of the reaction is directly proportional to concentration of the reactants in a reaction. Their product, this one as a reactant and this one as a reactant, raised to power their stoichiometric coefficients which are involved within that chemical equation. So within this chemical equation, stoichiometric coefficient of A is A, so stoichiometric coefficient of B is B. So this one is the law of mass action. Within these terms which we have put within these parentheses, they are the molar concentration. Earlier they were called as active masses. Now we will first of all take this point, active mass. What is an active mass of any substance? Active mass simply means it is molar concentration. Means concentration kept in terms of molarity, means molar concentration. We know that molar concentration means number of moles of the substance, number of moles of the substance dissolved per liter, dissolved per liter of the solution or per liter of the mixture. Active mass we can call number of moles dissolved per liter, means Here, if I will write this one, number of moles as N, after that this volume in liters as V, this one we call as active mass. We can now express this in this fashion. Number of moles we know, that is mass in grams. Taking this as absolute, WB mass in grams divided by its molar mass, then this one V volume here in liters. In liters, if I will take this volume in milliliter, so this term will be now WB divided by this one MB. After that I will write here V, or I will write in ml it. After that I will multiply this one by 1000. So this is the molar concentration. This is the molarity of the substance. This we call as active mass. Let us take an example so that we may be in a position to determine, to know what is an active mass of any substance. Suppose we have dissolved these 34 grams of this ammonia, means this one in 500 ml. These are present in 500 ml of the solution. Now, what is its active mass? What is its molar concentration? According to this relation, mass in grams, that is 34 divided by now molar mass. We know molar mass of this is 14 plus 3, that is equal to 17 into, after that this one as 1000, we have divided this one in, we have dissolved this one in 500 ml. So here 500 ml. That is simply equal to this one as 2 and this one also equal to 2, that is equal to 4. This is the active mass of ammonia if dissolved in 500 ml. So these are active mass, means 4 moles they are dissolved per liter. 4 moles of ammonia are now present in 1 liter, and that concentration term we call as active mass. Actually, it is the mass, it is the number of moles which are involved within a chemical reaction. If they are more in number of moles they are more in number, then rate of the reaction that will be more. So that is why this term is used within this law of mass action. If we will now apply this statement to this reaction, according to this statement means according to law of mass action, rate of the reaction is equal to this, means product of the concentrations of reactants raised to power their stoichiometric coefficients which are involved within that balanced chemical equation. Let us take now this example. Suppose we have these reactants again, A and B, and their stoichiometric coefficients, they are this one as N1 and this one as N2. After that, this reaction I will take this reversible reaction. Here are the products, they are C and this one as D. Suppose their stoichiometric coefficients, they are M1 and its coefficient, that is equal to M2. Then rate of the reaction is equal to, here I will write a constant that we call as rate constant of the reaction in the forward direction. Then the product of the concentrations of reactants. These are the reactants, their product. However, according to this law, the rate is directly proportional to product of the concentrations of reactants raised to power their stoichiometric coefficients which are involved within that balanced chemical equation. So this one is the rate law as per law of mass action for this reaction. So this is the law of mass action applied to this reaction. Here, this one, if we will write this one as Kf, means that is the rate of forward reaction. In the reverse reaction, we will also write this as a rate of forward reaction and this one as a rate of backward reaction. So I will write here constant this one as Kf and this one as Kb. Now, in the forward direction, these are the reactants. In the backward direction, now this and this, they are the reactants. Here I will write this Kb, after that concentration, this one as C, raised power this one M1 and this one as D raised to power as M2. So this is the law of mass action for this reaction for backward direction. If I have taken this reaction as an example. Similarly, we can apply the law of mass action for any reaction. For example, I will take here this reaction, this one N2 plus H2, or this one leading to formation of this one NH3. If we will balance this reaction, here are 2, so I will multiply here 2, then 2 3s are 6 here, or 3 2s are 6. So this one has Kf and this one has Kb. Now rate of the reaction according to law of mass action, that is equal to Kf. After that I will write here concentration of N2 raised to power 8 stoichiometric coefficient, that is equal to 1. After that multiplied by concentration of hydrogen 8 stoichiometric coefficient within this reaction, that is equal to this one. So this is the law of mass action for this reaction in the forward direction. We will take this point chemical equilibrium. In case of reversible reactions, let us take this example, general example. Suppose we have these reactants again, A and B, they react with each other, leading to formation of these products. C and D, they are the products. If the balanced chemical equation involves these coefficients, suppose again this one has N1, this one has N2. After that, this one has M1 and this one has M2. If this reaction is reversible, means first of all, when we mix these two reactants, they combine with each other, leading to formation of these products C and D. After some time, these two, when their concentration increases, they start to react with each other again, leading to formation of these two ones, A and B, means these products react with each other, leading to formation of these reactants. Then such a reaction we call as a reversible reaction. The reversible reactions, they occur mostly if the reactions are carried out in closed vessel. We know if reaction is carried out in an open vessel, that almost goes to completion. However, if the reaction is carried out in closed vessel, then the concentration of products that increases with the passage of time, and a stage reaches when the products, they start reacting with each other again, leading to formation of products. Then at that stage we can say that chemical reaction is in equilibrium, and that stage we call as chemical equilibrium. At chemical equilibrium, the concentration of these products as well as concentration of reactants, that remains unchanged, means concentration of products as well as reactants, that remains constant. Means here concentration, what is the concentration of these reactants A, B, C and D, and these one is products plus these reactants, their concentration at the stage of equilibrium, that remains constant. There is not any kind of change. For example, if the reaction is carried out at a constant temperature and equilibrium stage is reached, at equilibrium stage there is not any observable change in temperature. If this reaction is involving any color, for example, at the equilibrium stage, there seems to be no color change, not any other property. If we will measure any other property at equilibrium, it seems to be that there is no change in the property of that reaction. Just like we can take properties as pressure, we can take volume as property. If we will measure those properties at equilibrium stage, their value remains constant. This equilibrium is dynamic, means this reaction seems to be now not occurring, but in actual practice at microscopic level this reaction occurs, but with the same speed in the forward direction as well as in the backward direction. That is why we call equilibrium a process at that stage rate of forward reaction. In simple terms, we can say equilibrium state is that stage of the reaction at which rate of forward reaction, that becomes equal to rate of backward reaction. Rate of backward reaction, and that stage we call as equilibrium stage. This equilibrium stage can be attained from both sides. For example, if we will take these two ones as reactants, they taken in a closed vessel, they will react with each other, leading to formation of these. After some time, their concentration increases. When that increases to a limit such that they after that react with each other, leading to formation of these two ones. So this equilibrium process can be attained from both sides. However, the main important factor which affects this equilibrium, that is temperature. So temperature has an effect on this reaction. We will discuss the effects on chemical equilibrium or on equilibrium constant later on. First of all, I may say at a given temperature, the rate of forward reaction, if that becomes equal to rate of backward reaction, we can call that stage as equilibrium stage, particularly in case of chemical reactions as chemical equilibrium. So this is the definition of chemical equilibrium. At this stage, rate of forward reaction becomes equal to rate of backward reaction. So at that time, there is not any observable change. For example, we can say the concentration terms, means concentration of reactants as well as concentration of products, that almost remains constant. That remains constant at the equilibrium stage. Similarly, volume, pressure taken, whatever may be the property taken at equilibrium stage, that remains constant. As per a graphical representation, we know this one, rate of reaction. If we will take here concentration of reactants or products, concentration here on this axis we will take time. With the passage of time, concentration of reactants that decreases because we know they are converted into products. With the passage of time, concentration of products increases. However, in an equilibrium process, this stage is reached. Means now within this case, this is the concentration, means concentration of products that increases with the passage of time, and this one as concentration of reactants that decreases with the passage of time. Here now the concentration of both reactants as well as products that remains constant. That is not gets changed, means remains constant. So this stage we call as equilibrium stage. At that stage, the number of moles of reactants which convert into products, their number is equal to the number of moles of products which get converted into reactants. So in this stage, equilibrium stage, the rate of forward reaction that becomes equal to rate of backward reaction. Or we may take this one as in terms of rate of reaction. So this one as rate of reaction. Here rate of reaction, and here again this one as time. We know rate of the reaction. The graph of rate of reaction is just like this. With the passage of time, the rate of reaction that decreases. This one, rate of this reaction, rate of forward reaction. I will take this one, rate of forward reaction. In a similar way, this one. This is the rate of reverse reaction. First of all, this one, rate of backward reaction, this one. That increases when concentration, we know initially concentration of products that is smaller. So when their concentration increases, then products start reacting with each other. So their concentration increases. With the increase in concentration, their rate also increases. That increases to an extent such that now rate of forward reaction is equal to rate of backward reaction. At that time, we can say the reaction is in chemical equilibrium. Or we may take this graph. If we will take a catalyst, what is the work of a catalyst? If catalyst is introduced within a reaction mixture, that reaction is in chemical equilibrium, that reaction attains an equilibrium stage, then catalyst attains this equilibrium. This equilibrium is attained at an earlier stage. We know a catalyst changes the path of reaction, not changes the nature of reactants, nature of products within a chemical reaction. However, if chemical equilibrium is involved within a reaction, then catalyst attains that equilibrium. By introducing a catalyst, equilibrium is attained rapidly, means within a small interval of time. Within less time, this equilibrium is attained. This is the case when positive catalyst is introduced. When we introduce a negative catalyst means that again not changes the nature of reaction, that not changes the nature of products or reactants in a chemical reaction, but this time the equilibrium stage is reached, but at this one at much larger time, means some time is required. After that, this equilibrium is attained. So in this graph we have taken this one as a reaction without catalyst. So equilibrium is attained at this point. This one introducing a positive catalyst. So by introducing a positive catalyst, this equilibrium stage is attained at an earlier stage. By introducing a negative catalyst, again equilibrium is attained, but at a time which is somehow greater than this one. Again, we may say when a reaction occurs in both directions, means in forward direction as well as in backward direction, then a stage reaches when the rate of forward reaction becomes equal to rate of backward reaction. That stage we can call as chemical equilibrium. At that stage, there is not any observable change in the concentration of products as well as in the concentration of reactants. If there is color involving reaction, then no color change is observed at the time of equilibrium. Or if there are gases in a chemical reaction, then there is not any change in the pressure of the gases. So any observable property, if we will take that at chemical equilibrium, at equilibrium stage, there is not any change in that observable property, then that stage we can call as chemical equilibrium. Now we will take this point, what is an equilibrium constant for a reversible reaction. Let us take this reaction again, A plus B, that leading to formation of products, they are C and D. These are the stoichiometric coefficients. Suppose N1 here, N2 here, and here M1, and this one as M2. Then we know here is constant, we call that as Kf, and this one as Kb, means rate constant of backward reaction, this one rate constant of forward reaction. At equilibrium, we know rate of forward reaction. At equilibrium, this one. Rate of forward reaction, that is equal to rate of backward reaction. Now this rate of forward reaction, that is equal to, or that is directly proportional to concentration of reactants. This one concentration of reactants, their product raised to power their stoichiometric coefficients involved within that balanced chemical equation. They are here N1 and N2. So our F is equal to, I will write here this one Kf multiplied by this one A raised to power N1. After that this one B raised to power N2. Now rate of backward reaction similarly will be equal to this one Kb. After that these concentration terms, they are the concentration terms of products. Their product, this one raised to power their stoichiometric coefficients, they are M1 and M2. Now applying this equilibrium stage, we can say this Kf concentration of A raised to power N1 into concentration of B raised to power N2, that is equal to Kb concentration of C raised to power M1 into concentration of D raised to power M2. Now taking this ratio Kf, dividing this by this. So this one as Kb, now this ratio will be, this one will be divided here. So this one C raised to power M1 This one as D raised power M2. After that, this one concentration of A raised power N1. This one concentration of B raised power N2. This ratio we call as equilibrium constant of the reaction. So this law, this mathematical expression we call as law of chemical equilibrium. According to this law, the equilibrium constant of a reaction, that is the ratio of products of the concentration of products and concentration of reactants raised to power their stoichiometric coefficients which are present within that balanced chemical equation. So again I will state here this equilibrium constant of a reaction, that is the ratio of concentration of the products. Means here these are the concentrations of products. Their product, they are multiplied with each other. Their product raised to power their stoichiometric coefficients to the products of the concentrations of reactants raised to power their stoichiometric coefficients, and this ratio we call as equilibrium constant and denote that by Kc. C in the sense because these are molar concentration. These are active masses of the reactants and products involved within this expression. So that is why we have written here this Kc. This equilibrium constant, now the concentration of products, that is constant, concentration of reactants, that is also constant, that not changes at equilibrium state. So this ratio remains constant for a given reaction at a given temperature. Its value not changes if temperature is kept constant. So its value changes only when temperature of the reaction, means observable temperature, if that is changed, then value of this also changes. Otherwise, the value of this by changing concentration of reactants and products, this one not changes. Or even if we have a gaseous reaction, if we will change the pressure of reactants as well as products, the value of this constant not changes. It only depends upon one factor. That factor is the temperature of reaction. That we can say by means of one type equation. We have one type equation. By means of that we can say it changes with change in temperature. According to that equation, we know this one. Log of K2 divided by K1, that is equal to, this is the one-half equation, delta H divided by 2.303, or after that this one 1 by T1 minus 1 by T2. This we call as one-half equation. Within these, this T1 and T2, they are the two temperatures. If the reaction is carried out first of all at this temperature, at that time the equilibrium constant of the reaction is K1, and the same reaction is carried out at temperature T. At that time, equilibrium constant of the reaction, that is equal to K2. Now we will write this equation, log of K2 divided by K1 equal to delta H divided by 2.303, or after that this one as T2 minus T1 divided by T1 T2. Now if T2 is greater than T1, within this expression if T2 is greater than T1, so this term T2 minus T1 divided by T1 by T2, that is now, if this one is greater than this term is now positive, means positive. Now in this expression, if T2 is greater than T1, we can say T2 minus T1 divided by this T1 into T2, that is now positive. After that, the ratio will now depend upon the value of enthalpy, means if this one is positive we know that is for endothermic reaction. For endothermic reaction, delta H is positive. So after that, this one log of K2 divided by K1, that will be now positive. Positive means this one K2, log of K2 is greater than is greater than log of K1, or we may say K2 is greater than K1. In case of endothermic reaction, we know delta H is positive, then delta H will be, if positive, then this term is positive. So this ratio is positive. That means this log of K2 is greater than log of K1, or we may say this K2 is greater than K1. It means equilibrium constant of the reaction at T2, which is higher than T1, is more in comparison to the equilibrium constant of the same reaction if that reaction is carried out at T1. Means at lower temperature, if carried out a reaction at T1, T1 is lower than T2, its equilibrium constant is K1, and same reaction carried out at this temperature T2, T2 is higher than T1, then its equilibrium constant at this temperature is more. So for endothermic reaction, equilibrium constant of the reaction increases with increase in temperature. In case of this reaction, exothermic reaction, so this one will be negative and this one also negative. That means this term is negative, that will be negative when log of K2 is smaller than log of K1. So for an endothermic reaction, rate of the reaction increases with increase in temperature, or equilibrium constant at higher temperature is more than the equilibrium constant of the same reaction at lower temperature. However, in case of exothermic reaction, for which delta H is negative, the equilibrium constant of the reaction is lower at higher temperature and higher at lower temperature as per this equation. So equilibrium constant of the reaction depends upon temperature. Now this term Kc, we have written this one as Kc. These terms, they are the concentrations of products here, concentrations of products, their product, raised power their stoichiometric coefficient as M1, this one as M2, after that this concentration of reactants raised power their stoichiometric coefficients, and this expression, this ratio we call as equilibrium constant of the reaction. So in this way we can calculate equilibrium constant for any reaction. Let us take this example. For example, we have this PCl5 that dissociates into this one PCl3 plus Cl2. Now we will take it as this equilibrium constant, then Kc is equal to concentration of this one PCl3 into concentration of this one Cl2. After that we will divide this by concentration of these reactants, this one PCl5. Now for this general reaction I have taken this again, N1A plus N2B, this one equilibrium reaction, then here M1C plus this one M2D. We can take the equilibrium constant expression in terms of molar concentrations, in terms of pressures if they are gases within this reaction, or even we may take the equilibrium constant expression in terms of mole fraction. First of all, we know this one Kc, that is equal to the product of the concentrations of products, this one C raised power M1, after that this one D raised power M2 divided by this one concentration of A raised power N1, and this concentration of B raised power N2. This is the equilibrium constant of the reaction in terms of molar concentration. This reaction is a gaseous phase reaction, means reactants they are also in gases, or some of the products, one, two, or both may be gases. Then we can take the constant this as Kp. This is equilibrium constant of the same reaction in terms of pressure. At that time, instead of this, we write here this pressure term, means pressure of this C, this one raised power this one M1, after that this pressure of D raised power M2, then this one pressure of reactant A raised power its stoichiometric coefficient, that is N1. After that, this one pressure of B, then it is this stoichiometric coefficient as N2. So this one is the equilibrium constant of the same reaction in terms of pressure. This is the equilibrium constant of this reaction if the concentrations of these reactants as well as products within this reaction, they are taken as molar concentrations or they are taken as active masses. This one now in terms of pressures. If concentrations are taken in terms of pressures, means if they are the gas phase reaction, then we will take the pressures of reactants as well as products, then this ratio is the equilibrium constant of the reaction in terms of pressures of the reactants and products. Now we will relate these two, Kp and Kc. By means of this equation, we know as per ideal gas equation, PV is equal to nRT. After that, this pressure is equal to N divided by V or into T. After that, we know this one, number of moles per liter per unit volume, that is again active mass or that is molar concentration. Suppose this one as C molar concentration, after that this one as RT. Now taking within this expression, in terms of P, we will take this term as. Now in terms of P, we will write it as concentration. Means concentration of this one as C, concentration of C raised to power M1. After that, this one we know multiplied by RT, so this one R into T, that is also raised to power M1. After that, we will write D, means concentration of D, molar concentration of D, raised to power M2. After that, this one R into T multiplied, so we will write here R into T raised to power M2. Similarly, these one, pressures in terms of concentrations of reactant. So I will write here concentration of A raised to power N1, this one R into T raised to power N1, into concentration of this B raised to power N2, into this one R into T raised to power this one as N2. Now again here we will write this one C raised to power M1, after that this one D raised to power M2. This one here concentration of A raised to power N1, after that this one concentration of B raised to power N2. After that we know these RT and RT, they are here. Now R into T, these powers now added M1 plus M2, M1 plus M2. Similarly here R into T, after that this one, sum of the powers means N1 plus M2. After that I will write this one as this one, again that is equal to Kc, so I will write here this Kc. After that this term RT raised to power this one M1 plus M2, M1 plus M2. Now if this one taken into numerator, then its sign will be changed, so it will be now equal to N1, this one N2. This term we call, these are the number of moles of products, their number, these are the terms which are involved in case of reactants, so their total number of coefficients, means these are the coefficients involved within the balanced chemical equation, their sum. We will write this one as just like this, Kc, after that this one R into T raised to power delta N, this one. Now delta N is equal to number of moles, simply number of moles of products minus number of moles of reactants. Number of moles of reactants. This one delta N. As per delta N, now this one Kp is equal to Kc into R into T raised to power delta n. Now its value and its value, they will now depend upon the value of delta n. Whether this one is smaller or this one, that will depend upon the value of delta n. First of all, if delta n is equal to 0, means number of moles of reactants is equal to number of moles of products, then in that case Kp is equal to Kc into R into T raised to power 0. This one, we know anything raised to power 0 that is equal to 1. In that case, Kp is equal to Kc. So for example, let us take this reaction H2 plus, here I will take Cl2, this one as gas and this one also as gas, leading to formation of this. So for example, this one at HCl gas, here I will write twice. Then number of moles of reactants, 1 plus 1 means 2. Here also 2 moles. Means delta N that is equal to 2 minus 2 that is equal to 0. In this case, if we will take concentration terms and calculate this equilibrium constant, that will be same. If we will take pressures of these reactants and products, means Kp is equal to Kc. So in case of reaction in which number of moles of reactants is equal to number of moles of products, in that case Kp is equal to Kc. Now if delta N is greater than 1, means number of moles of products that is greater than number of moles of reactants. So at that time we can say Kp, here after that R into T raised to power delta N, means here this term is greater than 1. So this term will be greater than 1. Means greater than 1 here multiplied to this, at that time we can say Kp is greater than Kc. Now in case of if delta N is less than 1, means number of moles of products that is smaller than number of moles of reactants. Let us take this example, this one PCl3 plus Cl2, leading to formation of this PCl5. So in this case, number of moles of products that is equal to 1 minus this one, 1 plus 1 means 2. So that will be equal to minus 1. That is less than 1. Less than 1, if this one is less than 1, so minus 1 here means this one is divided by some term. So this value of this Kp at that time will be, at that time Kp is smaller than Kc. So in this way we have related Kp with Kc. Now we will relate this one, Kp and this constant Kx. Here this one is in mole fractions, means here are involved mole fractions of reactants as well as products. We know partial pressure of any component within a mixture, that is equal to mole fraction of that component. For example, this one has A component, so it is mole fraction A multiplied by total pressure. Suppose this one has total pressure. Now we know Kp, that is equal to, for this reaction, that is equal to Pc raised to power m1. After that this one Pd, pressure of product D raised to power m2, divided by this one Pa raised to power n1, this one as Pb raised to power this one as n2. Substituting within this, now this term, this one will be now xAp raised to power, instead of this I have written instead of C, so I will write here xc into total pressure raised to power m1. After that this one Pd means mole fraction of B into total pressure raised to power m2. Similarly this one aqueous A into P raised to power n1. After that this one aqueous B into P raised to power n2. So these are the terms, this one xc into xd divided by this one xa into xb. Their term, these coefficients are this one as m1, this one as m2, after that this one as n1 and this one as n2. Now here p raised power m1, mean here m2 means p raised power m1 plus m2. Similarly here p raised power here n1, that means n1 plus n2. This one we will denote by this kx. These are the mole fractions. This is the mole fraction of products, means their products, and these are the mole fractions of reactants, and this is their product. After that, each term raised power their stoichiometric coefficients. Then this denoted by kx. Now after that, this one p raised power m1 plus m2 minus n1 plus n2 means again delta n. This one. This is the relation between kp and kx. This one, kp is equal to kx, after that p raised power delta n. So again, whether this one is smaller or this one is more than this depends upon the value of delta n within a chemical reaction. Now after that, we will take the units of this one, kc. We know each term within the expression, equilibrium expression, means within equilibrium constant, we know each term is molar concentration. Molar concentration, again we know C raised power m1, this one D raised power m2 divided by this one A raised power n1, this one as B raised power n2. This one as mole per liter, this one mole per liter, this one also mole per liter, this one also mole per liter. Now the value will depend, unit will depend upon the values of m1, m2, n1, n2. Here difference is taken, means each and every term within this, that is equal to mole per liter. This one as mole per liter, this term. After that, this one m1 plus m2, m1 plus m2. And again, these two terms, this one mole per liter, this one mole per liter, they taken in the numerator now will be equal to n1 plus n2. After that, this is equal to mole per liter raised power delta n. So mole per liter raised power delta n will be the unit or equilibrium constant of any reaction. Let us take this one. Suppose this PCl5 that dissociates into PCl3 plus Cl2. This one. So here this one is more. This is 2 means delta n is equal to, these are 2, 1 plus 1, that is 2 minus 1. So 2 minus 1, that is equal to 1. In this reaction, the unit for this equilibrium constant is equal to mole per liter raised power 1, means mole per liter. In this way, we can calculate the unit of any reaction. In terms of this, we have to substitute the number of moles in this delta n. What is the value of this? Then if delta n is 2, then the unit will be mole square per liter square. Similarly, if it is equal to 3, then that is mole cube per liter cube. Or it may be equal to 0. If 0, then if delta n is equal to 0, then we know that units for this rate constant means they are equal to this mole per liter raised power 0, anything raised power 0, that is equal to 1. At that time, no units. Kc has no units when delta n is equal to 0. Similarly, we can say the units of this, Kp. Again, here the term, it is in terms of pressures. We know unit of pressure that we take as atmosphere, after that this one as delta n. Again, if delta n for a reaction that is equal to 0, then we know Kp is having no units. No units. If delta n is equal to 1, then we can say Kp is having unit of atmosphere raised to power 1, means atmosphere. If delta n is equal to 2, then we can say Kp is having unit of atmosphere square. In a similar way, for negative values, we can calculate the unit of Kp for a given reaction. After that, we will take another term. We call that as reaction quotient. Reaction quotient, that is Q. That is again the ratio of the concentrations, means concentrations of products, their product divided by concentrations of reactants, their product, each raised to power its stoichiometric coefficient in the balanced chemical equation. This one, again I will write here C raised to power m1. After that, this one D raised to power m2. This one as A raised to power n1. And this one as B raised to power n2. This quotient is the ratio at any concentration, means we will take either equilibrium concentration or we will take the concentration after some time when this reaction occurs, or we will take the ratio at some later time, ratio of the concentrations of products and reactants. If this ratio is taken at any instant, then that ratio we can call as reaction quotient. If now this one, Q, this reaction quotient is greater than Kc, means it is greater than, means this one is more than this. At equilibrium, we know this and this, their value remains constant. Here I mean to say, if this Q is greater than Kc, that means its value is more as compared to its value at equilibrium concentrations. So this reaction will proceed in this way, means it will consume products because their value is more. These are consumed. So this reaction will occur from this side towards this side. It will occur in the backward direction. If now Q is equal to Kc, at that time we can say the reaction is at equilibrium, means the concentrations now of this and this they are constant. Reactants as well as products, they are constant within this reaction. This case also arises if K is less than Kc, means this is not reached now within this reaction. Ratio is smaller than Kc. We know a reaction proceeds. Equilibrium is said to be a state which is the stable state in a chemical reaction. So, in order to attain the stability, the reaction will proceed so that its value will become equal to this. That will become equal when the concentration of products will increase. At that stage, we can say this reaction, if Q is less than Kc, at any instant of the reaction, that reaction will proceed towards this side.